Since the moment of creation, everything we do, every step we've ever thought of taking, every second of our lives depends on a giant nuclear reactor in the sky. It's a mind-blowing idea when you really start to think about it. The sun. We're more connected to it than we know. As Carl Sagan once put it, the cosmos is within us.
We're made of star stuff.
The carbon atoms in our body, they all got made in stars because there's none of it at the Big Bang. There's only hydrogen and helium, tiny bit of lithium, nothing else. And so it was all made in stars. And it's probably from different stars. You know, the atoms in your body, they're not all from one star that cooked it and then died. There'll be a mixture of stuff from many stars in your body. What more do you want? You know, when I see people who, I want more than that, there must be more to it. What do you mean? The ingredients in our bodies were assembled in the hearts of long dead stars over billions of years and have assembled themselves spontaneously into temporary structures that can think and feel and explore. And then those structures will decay away again at some point, and in the very far future there'll be no structures left. So there we are, we exist in this little window when we can observe this magnificent universe. Why do you want any more? But I think that's the journey that we go on. The real treasure, I think, is in that journey of trying to face the incomprehensible. It's in that realization that it's almost impossible to believe that we exist. That's what I think you miss out. I think if you decide to simplify it because you don't want to face that, you don't want to face the infinity that's out there in front of us, and you don't want to face those stories that you look at your finger and its ingredients was cooked in multiple stars over billions of years. That's to me a joyous and powerful thing to think about, and I think you're missing out if you don't want to face that.
In the grand scheme of things, our lives and our short lifespan are a blink of an eye compared to the seemingly unchanging nature of the sun. But it too has a life cycle. Stars are born, and after they spend all of their fuel, they die. Some more violently than others. Depending on the mass of the star, its lifetime can range from a few million years for the most massive to trillions of years for the least massive, which is considerably longer than the age of the universe. All stars are formed from collapsing clouds of gas and dust, often called nebulae or molecular clouds. Over the course of millions of years, these protostars settle down into a state of equilibrium, becoming what is known as a main sequence star. About 90% of the stars in the universe belong to this family, our Sun included. There used to be, and still is in many ways, a big misconception about how the Sun can, quote-unquote, burn for billions of years. But the Sun does not burn like we think of logs in a fire or paper burning. The Sun glows because it is a very big ball of gas, and a process called nuclear fusion is taking place at its core.
So the way the sun burns is by taking hydrogen, which is the simplest element in the universe, and just assembling helium, which is the stuff you get in party balloons, which is the next simplest. And when you do that, you release energy, and that's what the sun's doing. It's burning, though, 600 million tons of hydrogen every second. And at that rate, it's got about another 4 or 5 billion years to go. You can see it by watching how the sun wobbles, and so it rings like a bell. It's called helioseismology. It's like seismology on the Earth. You look at earthquakes, there's sunquakes, and by looking at those, you can see what the interior is made of, and you get the answer. It's got this helium and hydrogen in it.
Nuclear fusion powers a star for most of its existence. Initially, the energy is generated by the fusion of hydrogen atoms at the core of the main sequence star. Later, as the preponderance of atoms at the core becomes helium, stars like the Sun begin to fuse hydrogen along the spherical shell surrounding the core. This process causes the star to gradually grow in size, and as our Sun ends its life, it will transition into a red giant. This expanding Sun will engulf the Earth and any life that remains along with it. Stars with at least half the mass of the Sun can also begin to generate energy through the fusion of helium at their core, whereas more massive stars can fuse heavier elements along with a series of concentric shells. Once a star like the Sun has exhausted its nuclear fuel, its core collapses into a dense white dwarf, and the outer layers are expelled as planetary nebula.
Something like the Sun, when it collapses, there's a sort of a pressure, a force, if you like, which is caused by the fact that electrons don't like to be very close to each other. So it's called the Pauli exclusion principle. But essentially what happens is, so as they get squashed closer and closer together, they move faster and faster to sort of get out of each other's way, if you like. And that makes a force which holds them up. And so that creates what's called a white dwarf star. So you can have a blob of matter. They're about the size of the Earth, but they're about the mass of the Sun. That's for smaller stars. They end up as these white dwarf things, which are very dense objects. There's another version, which is called a neutron star, which is the same thing, but for neutrons. And they move faster and faster. So if it's massive enough that it overwhelms the electron thing, then the electrons crush into protons and turn into neutrons, and the whole thing starts again. And so a neutron star can be 1.5 times the mass of the Sun, let's say, but it can be about 10 miles across. So that's an incredibly dense ball of matter held up by the neutrons moving around. It's got a fancy name, it's called neutron degeneracy pressure. But if you go even bigger, then even that can't hold it up. And as far as we know then, there's no known force that we know of that can hold the thing up. If it's too massive, it collapses and collapses and collapses, and that's when you get a black hole.
Stars with around 10 or more times the mass of the Sun can explode in a supernova as their inert iron core collapse into an extremely dense neutron star or black hole. There is also a very energetic supernova thought to result from an extreme core collapse scenario. In this case, a massive star, about 30 solar masses, collapses to form a rotating black hole emitting twin energetic jets and surrounded by an accretion disk. It is a type of stellar explosion that ejects material with an unusually high kinetic energy. This explosion is known as a hypernova. Hypernovae are one of the mechanisms for producing long gamma-ray bursts, which range from 2 seconds to over a minute in duration. All observed GRBs have originated from outside the Milky Way galaxy, although a related class of phenomena are associated with magnetars within the Milky Way. It has been hypothesized that a gamma-ray burst in the Milky Way pointing directly towards the Earth could cause a mass extinction event. There is also another strange cosmic beast that is highly magnetized rotating neutron star that emit beams of electromagnetic radiation out of its magnetic poles. It is known as a pulsar.
So we see those all over the place. The first one that was discovered was called LGM1 because they spin very fast. And it was called LGM1 because it's a very regular pulse and they thought it was little green men. There's one called the Crab pulsar, which is in the Crab Nebula, which we saw the supernova explosion. So that's when one of these stars explodes at the end of its life and then collapses to form a neutron star. And we saw that in 1054 AD.
The periods of pulsars make them very useful tools for astronomers. Observations of a pulsar in a binary neutron star system were used to indirectly confirm the existence of gravitational radiation. The first extrasolar planets were discovered around a pulsar. Even though these cosmic phenomena are extremely far away, we can still make accurate predictions because we can see them. But what about something we can't see? Invisible stars that lurk in interstellar space.
And they're from collapsed stars. So they are stars at the end of their life, very bigger than the Sun, more massive than the Sun, but they run out of their fuel and they start to collapse because gravity squashes them. And if they're sufficiently massive, then there's nothing that can stop the collapse. And so they collapse, as far as we know, to a point, essentially an infinitely dense point. We don't know what happens right in the middle. But they collapse to such an extent that there's a region around it from which light can't escape. So nothing can escape. That's a black hole.
A rogue black hole is an interstellar object without a host galactic group. They are caused by collisions between two galaxies when the merging of two black holes is disrupted. It has been estimated that there could be 12 rogue black holes in the Milky Way galaxy. In January 2022, a team of astronomers reported on the first unambiguous detection and mass measurement of an isolated stellar black hole using the Hubble Space Telescope. But as far as our understanding of black hole goes, LIGO changed everything when they detected black holes merging.
There are two black holes and they were about 30 times the mass of the Sun each. And they were orbiting each other and spiraling in towards each other. And they accelerated. At one point they were approaching each other at 1/3 the speed of light. and they accelerated to 2/3 the speed of light in 1/10 of a second, and then hit each other. And the explosion, the energy release, it was something like 50 times the energy release that the power of all the stars in the observable universe glowing for a tiny fraction of a second. It's an unimaginably violent event, and that's why our detectors can see the ripples that makes in space and time. And we detected 2 neutron stars colliding. We saw that as well with it.